Hey guys, welcome back. So this is lecture 2 for Astronomy and Cosmology, and before we start I'd like to recap what we did in our last class. So the first thing we did was what the definitions for astronomy and the solar system. Then we talked about the formula linking intensity and power, right? And then we talked about what luminosity is and what radiant flux intensity is, and how luminosity is linked to power, and how radiant flux intensity is linked to intensity. And then we linked them with a formula, and we talked about how we can find out the distance to a distant galaxy if the galaxy has a specific star. And today we'll talk about what star that galaxy has to have. So let's begin with today's lecture. Okay, so we said that in order to find the distance to a distant galaxy, that galaxy has to have a specific star. This star right here, this is a very specific star. So this star is called a standard candle, right? And what would be a good definition for a standard candle? A good definition would be a star of known luminosity L is called a standard candle. STD is standard, a standard candle, right? So that's what a standard candle is. So if a distant galaxy has a standard candle, only then can we find the value for D, because the formula goes like F is equals to L upon 4 pi D squared, and as the definition says, it's a star of known luminosity. So you'll know the value for L. So if you know the value for L of a star, then you can find F with a telescope or a charged coupled device, and you can find D, right? So that's what a standard candle is. So in the exam, the examiner might say that there are two stars of similar luminosity. So I'll write down a question now. Okay, so that was a long question, but it's actually very simple. So I'll draw out a diagram so that it's easy for you to picture this. So let's read the question once again. So given that two standard candles, which means two stars of known luminosity, have the same luminosity, so these stars have the same luminosity, but standard candle X has a value for radiant flux intensity 20, and standard candle Y has radiant flux intensity 30, and the distance to star Y is 10 meters. Find the distance to star X. Okay, so what I'll do is, for example, this is me or you for that instance, standing here observing stars. Okay, so we're very wise people, we're observing stars at night, right? So this is star X, right, and this is star Y. Okay, so these diagrams are not drawn to scale, so don't judge these based on their size and whatnot. So this is star X, this is star Y. So I'll write down the data for each of them beside them. So they both have luminosity L, luminosity L. So they both have luminosity L, and then the question says the standard candle X has value for radiant flux intensity as 20. So we'll write down F is equals to 20, and standard candle Y has radiant flux intensity of 30, right? So F is equals to 30, and the distance to star Y is 10 meters. So this distance right here is 10 meters. Hence find the distance to star X. So we need to find this distance right here. So we'll call this D1. Okay. Now we have the formula. Sorry, we have the formula F is equals to L upon 4 pi d squared, right? Now you might say that if we don't have L, how will we find D? That's a valid question, but the question says that both stars have the same luminosity. So what we'll do is we'll form two equations, right? So the equation for X, star X, would be, so we'll make L the subject, star X, we'll make L the subject, hence the formula would be, F into 4 pi d squared, right? Then we'll put in the value for F, which for X is 20. So 20 into 4 pi d squared, right? And then we'll make an equation for star Y. The equation will be, again we'll make L the subject, F into 4 pi d squared, and L would hence be 30, but we know the distance to star Y as well, which is 10 meters. So 4 pi into 10 squared, right? Now we'll equate both these equations because the value for L for both of them is the same. So we'll call this equation 1 and we'll call this equation 2. Now we'll equate both these equations. So we'll take the equation for X here, 20 into 4 pi d squared is equals to 30 into 4 pi into 10 squared. If we want, we can cancel out the values for 4 pi because it's a constant, and then we can solve for d, and d can be the value, whatever value we find. I'm not in the mood to calculate, but yeah, so actually I don't have a calculator near me, so that's the main real reason. Okay, so I'm not as lazy. So we can find d from here. So if you don't want to go through all of this, a very simple solution is, whenever two stars have the same luminosity, you can just go ahead and use the formula F1 D1 whole squared is equals to F2 D2 whole squared. F1 being the radiant flux intensity of star 1, F2 being the radiant flux intensity of star 2, D1 being the distance to star X, D2 being the distance to star Y, because 4 pi and 4 pi cancel out, right? So you can use this equation for when two stars have the same luminosity. Okay, so that's that. Now we know how we can find out the distance, or we can also find out the radiant flux intensity of two stars which have the same luminosity. So that's one subsection done. That subsection was mainly based and related to how to find distance to galaxies and what standard candles are. Actually there's one more thing left. It's related to standard candles. It's called, this type of star is called a Cepheid variable. Okay, so Cepheid variable, it is a weird name though, Cepheid variable. Okay, so a good definition for this would be stars which are extremely luminous and undergo regular and predictable changes in luminosity. Forgive me for my handwriting once again. Stars which are extremely luminous and undergo regular and predictable changes in luminosity, right? So these stars can be used as standard candles because you'll know what luminosity they have at a specific time, because they have predictable changes in luminosity. Hence C variables, short for Cepheid variables, usually commonly used as standard candles. And one more thing, I'll show you a graph to demonstrate demonstrate their changes in luminosity. So I'll give the y label, or the y axis, the label luminosity. Oh my god, horrible writing. Luminosity and time on the x-axis. So the changes they have in the luminosity goes like this. So this is how they change the luminosity. So from the graph you can predict what luminosity they would have at a specific time. So the x-axis has the label time and the y-axis is luminosity. So this point they have maximum luminosity, minimum luminosity. So this is something you should know for extra knowledge. And Cepheid variables are not directly in the syllabus, but they are something on the side, something that you should know. Okay, so to summarize what we did today, I'll just write a short summary for today as: number 1, Cepheid variables. We talked about Cepheid variables, how they're stars with known changes in their luminosity. This graph indicates just that. So we did Cepheid variables. We talked about how Cepheid variables can be used as standard candles, right? And this helps us find / measure distance to a distant galaxy. So if a distant galaxy has a standard candle or has a Cepheid variable which we're treating as a standard candle, we can find out the distance to that galaxy. So at the end I would just like to do one short question. So I'll write down the question. You can fast forward this. Luminosity of a star is given as 6 into 10 raised power 3 10 raised power 31 watt. Radiant flux intensity is given as 1.9 into 10 power minus 9 watt per meter square. Use the data to find distance of star. Right, it's a very basic question. We just have to use the formula that we've been using since the previous class. So F is equals to L upon 4 pi d squared. So F is given as 1.9 in 10 raised to power 10 raised to power minus 9, 1.9 into 10 raised to power minus 9. L is given as the luminosity of the star is given as 6 into 10 raised to power 31. 6 into 10 raised power 31, and we have to find the distance d, 4 pi d squared. We make d the subject and we get 5 into 10 raised power 19 meters as the distance of the star from wherever you're observing the star, right? So that wraps up our first main subsection of this chapter, which was to find the distance to a distant galaxy. So all of the stuff we've done in the first lecture and in this lecture was all linked to finding the distance to a distant galaxy. So basically the distant galaxy has a standard candle of which you know the luminosity of, and of which you can find the radiant flux intensity of through a telescope or a charge coupled device, and hence you find the distance to that galaxy. In the next lecture we'll look into how we can find out the radius of a star, and in the final lecture we'll talk about Hubble's law and about the Big Bang theory. So I'll just write down the stuff we have done and the stuff we have to do. I'll write down the subsections actually. So number 1 was the distance to galaxy. Number 2, these are the subsections of the chapter. Radius, and many things come under each subsection. Radius of a star. Number 3 is Hubble's law. Number 4 is, and the Big Bang theory and the Hubble's law are very closely linked. Big Bang theory and some other stuff linked to Big Bang theory. So we are done with the first subsection, which was finding out distance to the galaxy and other stuff like standard candles and Cepheid variables linked to this subsection. I hope you enjoyed this video. I hope you learned something. So don't forget to like, share it with your friends, and please do subscribe as well and hit that bell icon. So thank you for watching. See you in the next video.